Okay, we're on to the fourth and final thing that could happen when we do partial fractions. I've paused here on this slide because I want to revisit this technique of integration, where we have completed the square in the denominator for some irreducible quadratic, and we now have the integral of cu plus d divided by u squared plus a squared du. Maybe your u is worth exactly an x. Maybe your u is worth twice an x. This same idea is going to apply every single time. I wanted to repeat this formula because it bears repeating, and somehow I suspect that people might have skipped the last minute or so of that previous video. Gosh, why would I think that? Anyway, the technique here is to split at the numerator of this fraction. This integral at the left is equal to c times the integral in the middle, u divided by u squared plus a squared. And then I'll get my constant out over here. This is plus the integral of constant d times the integral of 1 divided by u squared plus a squared. This integral in the middle I can do with a substitution. I might say that w equals u squared plus a squared. dw is twice of a u du. That should be old hat at this point. The new stuff, the relatively new stuff, is recognizing that 1 plus u squared plus a squared is the derivative of the arctangent function. That means the integral of 1 over u squared plus a squared is going to be the arctangent function, just with this parameter a here controlling the coefficient of the arctangent function. This is the step every single time we integrate rational functions that look like this. Every single time we're going to split that numerator, use a u substitution on one of the pieces, or a w if you've already used the variable u, and we're going to use the arctangent formula on the other of them every single time. Now, with that in mind, we can actually talk about the last possible thing that could happen. What happens if we get irreducible quadratic factors and they repeat? Oh my goodness, what a horrible fate. So what is this going to look like? Again, I've got some quadratic, ax squared plus bx plus c, and it'll be raised to some power r. And again, I know that this is irreducible because inside of my quadratic formula, I've got the square root of some negative thing. I don't even need to set up the whole quadratic formula. I just need to check, is b squared minus 4ac positive or negative? Or 0. 0 can happen as well. But it's only the negative value of this formula that gives me irreducible quadratics. Moving on. So what we're going to do is actually pretty much the same thing that we do for the linear case. You probably saw this coming. Whatever that power is, that power r, I'm going to have one partial fraction for each different power of my quadratic. So I'll have some ax plus b divided by the quadratic. I'll have some a2x plus b2 divided by the quadratic squared. I can have that over the quadratic cubed and so on. This is the formula I'm going to use in the decomposition. Again, this looks really hairy, and it'll work for r equals 1,000. I don't want to do r equals 1,000. I certainly don't want to grade it, so I'm not going to make you do r equals 1,000. But it should be at least encouraging that this formula could work there in theory. So what I claim now is that this same integration by completing the square, that's going to work on every single piece. So let's take a look. Here is a partial fraction. It's already been factored for us. And just to double check that the degree of the numerator is 3, the degree on the denominator is, so I've got a 1 here, I've got a 1 here, so together that's 2. I've got 2 more here, so together that's 4. And here I've got x squared, which is then cubed, so that's got to be 6. Looks like I've got degree 10 on the denominator. Okay, we can work with that. So these first three terms in the factorization are not repeated. So I'll have an a, numerator of a for that denominator of an x. I'll have a numerator of a b, a different constant for that denominator of an x minus 1, and so on. Numerator of cx plus d for the denominator x squared plus x plus 1. Looking good so far? This is just the same stuff from my last 3 videos. For the new stuff, my quadratic here, x squared plus 1 cubed, third power. I'm going to need 3 more partial fractions. One of them has a denominator x squared plus 1. One of them has a denominator x squared plus 1, which is then squared. One of them has a denominator x squared plus 1, which is then cubed. Now, that would be the decomposition. Let's maybe wind back to an easier function so I can actually do the integral and show you how the integral step is without crowding out the entire slide in scratch work. So this integral is the integral of 1 minus x plus 2x squared minus x cubed. That's my numerator. The denominator is the quantity x times x squared plus 1, which is then squared. So it's very nice that this has already been factored for me. Degree on the numerator is 3. Degree on the denominator, if I multiply this all out, would be 5. I have an x squared here, but it's squared again, so that gets me up to the 4th power. Times 1 more x gets me up to the 5th power. This is a degree 5 on the denominator, which is good. 3 is less than 5. That's what I want. If you're looking for fancy vocabulary, I could say this is a cubic divided by a quintic, but I'm not grading on fancy Latin ordinal names, so don't worry about that. In the decomposition, I have a constant a divided by my x. I have that because of the factor of x right here. I also have this irreducible quadratic. Do I know it's irreducible? Why, yes, I do. X squared is my upwards facing parabola. If I lift it by 1 unit off the x-axis, it does not have any roots anymore. That's my geometric reasoning. So because this is squared in my factorization, it needs 2 partial fractions. I'll call this bx plus c divided by an x squared plus 1. And I will have a dx plus e divided by x squared plus 1 squared. Following along? Now, can you guess what comes next? If you said multiplying by the denominator, then you guessed correctly. Or you've been paying attention to the videos, which, I'd like that better than guessing. So what do we get? On the left side, we get just that cubic, right? Negative x cubed plus 2x squared minus x plus 1. On the right-hand side, there is a lot of bookkeeping, but it's okay because there's cancellation. I used to have a divided by x. That x canceled, so I'm left with a times x squared plus 1, which is then squared. And so on. In the middle term, I have some more cancellation here, and I pick up an x times x squared plus 1. And then my final term, the quadratic cancels, and I'm just left with dx plus e, and that quantity is multiplied by x. There's a lot going on there, but the work is tedious, not difficult. There's a difference, right? So we're not doing conceptual heavy lifting when we multiply these things out. It's just a process that requires a little bit of attention and a little bit of time. It's going to be okay. Now, whoever wrote these slides did not include all the scratch work because they want to pretend that they are a wizard. But if I multiply all this stuff out, I should get this bottom line here. A plus b times x to the 4th power. Well, where do they come from? Here's an x to the 4th. I can't click on things. Here's an x to the 4th. It's multiplied by an a. Here's an x to the 4th. It's multiplied by a b. So that makes a little bit of sense. Where are my x cubeds? Well, they're certainly not here or here. I've got a single x cubed multiplied by a 3. Where are my x squareds? Well, I've got 2 times a of them here. I've got 1 times b of them here, and I've got 1 times d of them here. So that's my coefficient of x squared. Where are my x's? There's a c times an x and an e times an x. Where are my constant terms? The only constant I've got is in this first set of parentheses right here. That'll be an a. So with very careful bookkeeping, I multiply this all out. This polynomial on my first line, normally I'd call it the left, but there's not enough room on the slide to do left and right. This very first line polynomial is equal to this very last line polynomial. So I can match coefficients. This a is the constant term of the polynomial at the bottom. It has to be equal to the constant term of the polynomial at the top. A equals 1. This is the very same idea I've been using this whole lecture, only slightly more complicated and asking for slightly more attention that we don't make a mistake. What do I see here? I've got x to the 4th power. I don't have any x to the 4th powers on my top line. That tells me a plus b has to equal 0. So we do this the whole way through, and this is the system of equations that we've got. There's 5 of them. There should be 5 of them. I have 5 different variables. But it turned out pretty well, actually. 2 of them are already done. A is 1, C is -1. Oh, well, then E has to be 0, just automatically. Looking at that, C plus E equals -1. And B has to be -1. This system pretty much solves itself. So we claim that the solution is A equals 1, B equals -1, C also equals -1, D equals +1, E equals 0. So what does our integrand look like? It looks like this. So this rational function breaks down into these terms: 1 divided by x minus x plus 1 on x squared plus 1, plus an x divided by x squared plus 1, which is then squared. As before, I'm going to break down each of those pieces. Antiderivative of 1 divided by x is the natural logarithm of the absolute value of x. Here again, for this second integral, the integral of x divided by x squared plus 1, I'm going to use a u substitution, and I get as my antiderivative the natural log of x squared plus 1, and I pick up a 1/2 from my conversion factor between my du's and my dx's. This integral is super duper simple. Integral of 1 divided by x squared plus 1. That is my tangent formula. And not only that, it's a constant a equals 1. So my antiderivative is just the tangent inverse, or the arctangent, if you prefer, arctangent of x. I do prefer, so I'll say arctangent of x. And finally, I have the antiderivative, x divided by x squared plus 1 squared. This one, again, is a u substitution. So what have I got there? U equals x squared plus 1. A du is worth twice of an x dx. So my antiderivative is going to be -1 divided by 2 x squared plus 1 squared. Again, sort of shoving the scratch work off the side so we can pretend to be geniuses. In reality, it would take a while, and I am running out of time for this lecture. But these steps are tedious. They are not difficult. They acquire care and attention and time so that we don't make mistakes. But every single step that I'm doing is a small step. And every single step that I'm doing builds on the tricks and the techniques and the mathematics that we already know. This stuff is within our reach as long as we break it down into small pieces and do every small piece in its own time with the care that each piece requires. And don't forget the concept of integration.